Okay, we're going to deal with the kind of major idea behind how do you do measurements with continuous data. And the big tool here is what we call a density curve. And the density curve that we tend to use is what's called the normal curve because of how many things have central tendency. And later on, we're going to see that samples that come from the same population tend toward the mean of that population's data. So the normal curve becomes kind of important because it is the curve that represents central tendency. All right, so what is a density curve? A density curve has two big characteristics. If you look at all of the possible outcomes, the area under the curve itself always has to be positive because you can't have a negative outcome. And the area under the entire curve has to equal exactly 1. Now this means that if you measure any interval of outcomes, you're going to get the probability that something is falling on that interval. So we're going to play around with that a little bit in class and look at some density curves, things like a uniform curve or the normal curve or just some other just weird shaped ones and show you how these things work. But it's basically you take a chunk of the curve, you measure the area under that chunk of the curve, and it tells you the probability of a data point lying within those two x values. So we'll look at that in class a little bit more. So when you have a density curve, they look like, okay, so this is like a density curve that's skewed to the right. Okay, so if you look at this one here in the picture, the area under this curve is 1. Like the area between here and here is the probability between these two x values. We have a mean and a median for these density curves. The mean is like if you were to turn this thing into a solid, it's where the solid would balance. Okay, so think about putting this thing on like a seesaw or a teeter-totter. Where would you have to put the center, the fulcrum, so that it would balance? That's where the mean lies. Okay, the median makes it so the area from the left side to your median, it comes out as 0.5 or 50%, and then the area from the median all the way to the right side is 50%. So the mean is where it balances. The median is where the areas are equal on either side. And note, because I'm skewed right here, the mean is further to the right than the median, right? So if I move this mean further that way, this tail is going to get longer. Okay, so there you go. All right, so what is the normal curve? A normal curve is a distribution curve, a density curve that has a bell shape, and it is single peaked, and it is symmetric. And it's determined by two numbers. It's determined by its mean, which will also be its median, so it's going to be one and the same, and another number called the standard deviation. So this is an example of a normal curve. It's some sort of vocabulary curve where the mean is at 6.84 and the standard deviation is each of these lines going out. So to get from 5.29 to 6.84 is one standard deviation. Okay, so we get what's called the empirical rule, or sometimes they call it the 68, 95, 97, 99.7 rule. And the best thing to do is just kind of look at this drawing down here. If you think about this, the probability of being within one standard deviation of the mean is that 68% of that population is going to be between -1 and 1. Their z-score will be between -1 and 1. It will be one standard deviation from the mean. 95% of the population is going to be between -2 and 2. So it's almost everybody, 95%. And you can see the tail's getting smaller as we're going along. So to get to 3 standard deviations, 99.7%, almost every single value is going to be within 3 standard deviations of the mean. So 68 is where the typical values are. Remember, one standard deviation is how far you expect the typical values to be from the mean. 95% means like we're almost all of them. 99.7%, 3 standard deviations from the mean, is like way out there, and it's almost every single member of the population is going to be within 3 standard deviations of the mean. Okay, so the standard normal distribution, okay, so this is actually how z-scores are distributed, is a normal curve, so it's a bell-shaped curve where the mean is 0 and the standard deviation is 1. So this is actually the distribution of of z-scores, right? Or the distribution, like, yeah, it's going to be the distribution of z-scores actually looks like this. So it's going to have a mean of 0 and a standard deviation of 1. 1 is 1 standard deviation away. 2 is 2 standard deviations away if I have a standard normal distribution. So we'll look at how that's relevant. It's not as relevant as it used to be because you used to have to turn everything into z-scores and then calculate. But because our calculators are a little more sophisticated, we don't have to worry about that anymore. A normal probability plot. Okay, so this is like an optional topic in the AP Stats environment. You are allowed to use a normal probability plot to assess the normalcy of a curve. However, you do not have to do this. So there are other ways of assessing normalcy, but this is probably the easiest one. Okay, so the normal probability plot is going to be a scatter plot, which we haven't talked about scatter plots yet, but it's going to be a plot where each of the points is the data value from the set and its expected z-score. Now, if I plot that and I get a line, if those plots like look like they're all like linear, then I can assume that the data set is roughly normal. If that data set curves, then I can't make that assumption. Now, we're going to see this in class, and I'm going to have you guys do this in class, but I'm actually going to bring up the calculator right now, so if you'll let me pause for. Alright, so I'm going to look at my calculator here, and whoops, there, the calculator went away, there it's back. Alright, and I have some old data in here. It was something that we did in class maybe yesterday or the day before where I loaded a whole bunch of data into L1. So I'm just going to use that data and try to assess its normalcy. So what I'm going to do here is I'm going to go second stat plot. I'm going to turn on plot 1, and what I want, so there's a scatter plot. This is kind of what I want, but not really. That's a polygon, that's a histogram. These are the 2 box plots that we've already used. This one over here is the normalcy plot. So I'm actually going to turn that last one on. My data is in L1. My data axis is always going to be the X. It gives me a chance to pick my marker. I like the pluses. It just makes things look a little prettier to me. So I'm going to hit zoom 9, which is going to make this plot. And if you look, okay, so it took the data, so the x's are the values for L1, and the y's are the expected z-scores, right? So z-score of 1, z-score of 2, z-score of 3. Remember, most of the data is going to be within 3 standard deviations of the mean, right? So that's how the z-scores should work out. And if you look, this is not very linear. This kind of seems to make like a swooshy curve going up. So this data I would assess as probably not fitting the normal curve very well. If you have data that fits the normal curve, these little stars are all going to just make a nice, neat little line going through the normalcy plot. So this is an easy way to determine whether or not a set of data actually fits a normal curve. We're going to take a look at some of that in class and do some visual assessing of normalcy. It is allowed on the AP exam, but this is not a required topic. So there are other ways to assess normalcy. We'll get into those later in the year, but this is a quick and easy technological way to do it. All right, so there's an overview of density curves and normal distributions, and we'll do a bunch of work with these over the next couple of class periods.